right, folks, here we go. Type 2 collision today. In the past, we've referred to this as the bullet and the board. Um, so basically, the big difference here between today's lecture and yesterday's lecture is that now we're going to introduce friction to the mix. Okay, so we're still going to have a moving object collides with a stationary object, and then they both move off together. All right, so a couple things to be aware of here for us. What we're going to see now is that is that now we'll have to find the force of friction. So there's going to be a coefficient of friction that's going to be presented to you, which you have to use. So you're going to calculate the force of friction. You're going to, just like we've done in the past, mu mg, going to be on a flat surface. You're going to have to calculate the work done from friction, right? Force times distance. And then the distance becomes important for us because that tells us how long, excuse me, that friction is in contact with the object. And because this really turns into a sliding problem at the end, what ends up happening is that we see the sliding force or that friction force is the only force that we have. So it's the only thing that's doing work for us. All right. So what's the same? We're still going to calculate momentum before and after, because remember, conservation of momentum states that momentum is neither created nor destroyed, just transferred between the objects, right? And that's why we use the momentum to switch between, because the kinetic energy can be lost, because energy in its form can be transferred into something else, especially in this case, it's going to be transferred into heat or friction or something like that, okay? So when we look to make that jump between the two, before the impact and after the impact, that's why we have to use momentum. All right, so here we go. We say a bullet is fired, something else there. Oh, no, okay. A bullet is fired horizontally into a wooden block that is at rest on a horizontal surface. The bullet embeds itself into the block, and the bullet and block slide some distance to eventually end up at rest. So, a couple of things that you can be aware of, all right? We can find the mass of the bullet, or if we have the mass of the bullet and the mass of the block, if we know the sticky grabbiness of the surface, the coefficient of friction, and we know the distance, we can work backwards to determine velocity. We can also, if we know the velocity, use all of those same things to work back and find the distance that this thing should travel. It gives us a little insight into, if we know, for example, with a gun, muzzle velocity or exit velocity of the bullet, then we can work backwards from that point on, okay? So basically, here's what we get, okay? We shoot that bullet, it's fired at a stationary object or a stationary block, and the bullet and block slide to a stop, all right? Again, that's why we tend to call this the bullet and block problem. It could be anything where, like a car in real life with the brakes on, we hit it and then those two slide to a stop. And we can figure out the friction between the tires and that stuff, right? So again, even though we're looking at this as far as like using a bullet, there are other applications to it, all right? So here we go. All right, so now for us, actual data in actual run. So we find that a mass of our bullet is 40 grams. Now, please understand, we're not going to start off giving you kilograms for bullets. If we give you kilogram for bullets, those are crazy huge bullets, because 1 kilogram is 2 pounds. Think of a 2-pound bullet. That's like, what? Revolutionary War, losing limbs and stuff like that. That's like tank artillery. Those are crazy huge bullets. All right. So the mass of our block, in this case, is going to be 1.96. The coefficient of friction between the surface is 0.5. And then our block travels 0.4 meters. All right. We want to determine the velocity of the bullet before the impact. All right. So as I saw it, here were kind of my thoughts. First and foremost, we're going to calculate the work done by friction. That's the first thing that we have to be able to do, is figure that out. Once we know the work done by friction, this is going to be we can then calculate the change in kinetic energy, all right? We can then determine the velocity of the bullet and block after the impact. Then we can get to the momentum of the bullet and block after the impact. Now, hopefully what you're seeing here is that all of this stuff is after the impact, because we know how far the block slid. Right? Once we get to that point of knowing how fast or how much momentum we had, then we can start switching. and determine the momentum before. Remember, the only way to trade between the before and the after is by using momentum or impulse for us, okay? And then we determine the velocity of the bullet before impact, all right? Here again, look at the steps of the problem. Start with A, don't start with D, all right? Start with A. So, calculating the work done by friction. Here we go, all right? So, work done by friction, work is equal to force times distance, right? So in this case, because we're using friction, we have to find the force of friction, all right? Force of friction is mu mg. You can go mu times the normal force if you wanted to. So what we want to know is okay, what is sliding? It's not just the bullet, it's actually the bullet and the board. So that's where this comes from here, right? So when you look at this 0.04 and this 1.960, that is the bullet and the board. Notice I changed the bullet into kilograms because I have to use kilograms for this, right? So my gravity is measured in meters per second. And in order to adjust everything, we have to have kilograms, okay? So we take 0.5 times 0.04 plus 1.96 times 9.8, and then the back end here, that is my distance, right? That's my delta x, delta d, whichever way you want to look at it, okay? We find that the work done by friction was 3.92 joules. Okay? So now that we understand how much work was done by friction, that was the work of friction to take it from the beginning of the impact all the way to stopping it at the end. That's how much work was done there. All right. We then have to look and say, okay, calculate the energy lost to friction. Now, here again, what we want to think about is that where is this energy going, right? Because the block is moving, it's kinetic energy, right? Friction is going to turn this thing into heat. So what we want to know is using one of our equations from one of our previous chapters, work is equal to the change in kinetic energy, right? So our work here is that kinetic energy of the bullet and the block, right? So what we see is that once we know the work, we know the kinetic energy, right? That's the change in kinetic energy force, right? It had to have 3.92 joules of energy in order to be able to move that distance. Remember, in order to do work, you have to have energy. All right. So onward, part C then. Calculate the velocity of the bullet block. Now, it would be great if we knew the momentum, but at this point, we don't know the momentum. All we know is kinetic energy at this point, right? Because we just calculated the work, which turns into kinetic energy, right? So in order to do that, we take our kinetic energy and we're still in the bullet block phase, right? So we know that we had a max of 3.92 joules of energy. That's equal to a half times the mass of the bullet and the block. So you got your bullet, you got your block, right? And that's times v squared, right? What ends up happening, 3.92 divided by half, divided by 2, square root of that, we end up seeing that we get just under 2 meters per second. That is the kind of immediate velocity just after collision, right? Now, again, that energy is going to be gone. As soon as we get to the tail end of it, it's not going to have any energy left because it's going to stop, right? We lose all of that energy of motion to friction to heat. Okay? So this is just the momentary second after, or the momentary brief instant in time after it's hit. All right. Part D, calculate the momentum. This becomes big because our momentum is not going to be lost. We're going to transfer momentum 100% evenly. All right. So just after the impact, we want to use now that velocity that we just found. So the momentum of the block is, or the bullet in the block is equal to the mass times the velocity. So what we do is we take the mass of those two together yet, multiplied by the velocity of 1.98 that we just found. All right. Once we know that there is 3.96 kilogram meters per second just after the impact. This is a big deal for us because what we found is the total amount of momentum in the system, meaning that this 3.96 is all the momentum that we have for it. All right. And it's all after the impact now. So what we have to figure out is, where did this momentum come from, right? This momentum came from the bullet. Again, if the wooden block is at rest, like we see up here, then all of this momentum came from the bullet, right? So our bullet and block got its momentum from the bullet. So what that means is our bullet and block are 3.96. Our bullet is also 3.96, just the moment before impact. So if we were to be looking at, a timestamp of this, we'd see the bullet apart and then the bullet and the block, right? Just after the impact of it, as it starts to move it, we would see those two things are going to both be 3.96 kilogram meter per second. All right. So if we know the momentum now of the bullet, what we can do is we can calculate the velocity of it. Again, because momentum is conserved, we're going to say, all right, 3.96, that's equal to 0.040 times v. So what we end up seeing is the velocity of our bullet ends up being about 98.99 meters per second. Okay, let me just verify that. 3.96 divided by 0.040. Yep, it's basically 99. Okay. So what we end up seeing here is, to kind of recap it all for you. All right, and I'm going to kick out of here and just show you this. Discard that. Okay, so the path that we took to get here, right? We calculated the work done by friction. All right, we calculated the change in energy, which was the same as the work, because the work needed that energy to slow it down. We determined the velocity of the bullet by using the energy of motion, kinetic energy. We then determined the momentum of the block and bullet because we knew how fast it was traveling the instant after it impacted. Right? Then we were able to say, okay, if we know the momentum of it after the impact, where did all that momentum came from? It came from the bullet itself. And then we were able to find the velocity of it. Okay? Here is another example for you of this. This one is up on Schoology. Check it out. Similar setup, similar way of running this thing. See if you can figure out the answer for this one, and then also make sure you're working on homework at some point in time too, because that's got a little bit of a twist on it. All right, bye-bye.